This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Attempting to merge the two most successful theories in physics causes the underlying mathematics to break down into paradoxes. General relativity operates on the smooth, continuous geometry of a pseudo-Riemannian manifold. This metric-dependent bedrock is the only way it can calculate space-time curvature. The standard model of particle physics utilizes a completely different architecture. It houses gauge fields within Ehresmannian auxiliary fiber bundles, mathematical structures that exist independently of the space-time metric. This foundational divide is documented here as the twin origins problem. Point 1 shows space-time emerging from a Riemannian manifold, while point 2 shows gauge groups emerging from separate vector bundles. They occupy the same universe, but originate from disconnected substrates. Trying to quantize gravity over this broken geometric foundation forces the equations into infinite regressions. The standard model requires dozens of internal degrees of freedom to account for particle symmetries, dimensions that a four-dimensional manifold cannot accommodate. By treating four dimensions as the fundamental floor of reality, we are forced to treat gauge fields as auxiliary additions rather than native components. The observers provides the structural pivot needed to resolve this dimensional mismatch. This architecture utilizes a 14-dimensional arena, denoted as Y14, that exists as the overarching geometry above our observable reality. Strict pullback maps act as mathematical tethers. They project the complex geometry of this 14-dimensional arena down onto a 4-dimensional observer space, denoted as X4. Projecting from this higher space allows metric tensors and gauge fields to derive from a single unified geometrical source for the first time. To formalize this architecture, the Pasev geometric structural layer closure rebuilds the physics blueprint from bedrock mathematical axioms. Success depends on establishing a new foundation that remains stable even at the most extreme scales. We begin by entirely removing the continuous space-time manifold in order to clear the foundation for a new geometry. The replacement is an ordinal base space, defined by a mathematical triple, a set, a topology, and a strict order structure. Every non-empty subset within the space possesses a least element, ensuring the structure always has a definitive floor. This ordering terminates the threat of infinite descending chains. The regression hits a hard floor and halts. The ordinal base provides a foundation that remains internally consistent without the possibility of systemic collapse. We now build the total space vertically on top of the base. Every individual point across the base space is assigned an independent mathematical fiber. A surjective projection mapping rigidly connects every point in the high-dimensional total space back to its specific origin on the base. Maintaining local triviality across these fibers ensures structural compatibility throughout the entire framework. This architecture allows the 14-dimensional overarching space to map flawlessly down to our 4-dimensional reality. In complex geometries, dynamic forces often warp the underlying bundles, creating systemic instability. We test the structure using a global transformation operator, mapping the total space back onto itself. Stability is maintained by an absolute mathematical constraint, pi composed with t equals pi. Because the total space must project back to the same base points after a transformation, the operator is mathematically forced to preserve the internal structure of every individual fiber. Physical properties housed within these fibers are globally invariant. Physical laws remain unchanged across the observers. The abstract geometry finally becomes truly dynamic when the previously inert mathematical lattice ignites with raw physical energy. We introduce the directional operator, which acts on bundle sections to define connections between fibers. This operator defines the gauge fields, the structures that govern particle interactions and transport. Measuring the tension between these connections gives us the curvature operator. This curvature defines the field strength of the system. Pairing these field sections induces a symmetric structure, generating the metric tensor. Gauge and gravitational structures emerge as necessary geometric consequences of the bundle's internal logic. How does the system parse this high-dimensional data to identify observable physics? The Pasev closure utilizes an algorithmic extraction mechanism known as spectral sequences. The process begins with a filtration, which creates a hierarchical nesting of the total generated space. Boundary maps then algorithmically filter out chaotic, non-persistent data as the sequence iterates. The loop terminates when the sequence stabilizes, isolating the stable components. These stable terms represent the persistent structural invariants, the actual observable physical features of the universe. The final geometric architecture achieves phase 1 closure, locking the entire structure into a stable and verified configuration. The internal structural consistency is now mathematically proven. The foundation is secure. The framework is limited to formalizing the geometric layer. It intentionally lacks a quantum operator formalism, and it stops before providing a complete derivation of the full Einstein field equations. This modularity is intentional, allowing the framework to serve as an extensible foundation rather than an isolated theory. Phase 1 of the Pasev geometric structural layer is closed, establishing the mathematical starting point for Phase 2 development.